Hello, my name is Gregory Daniel Ziegler, and I'm a student in Professor Ruspa Hafnazar Kochesarai's 470 Human Factors in Cybersecurity class. CyberSecurity Engineering, CYSE 470, is a class that discusses the human factors of cybersecurity engineering and how to best mitigate those human factors in developing cyber systems. Human beings are in fact the weakest points in cyber systems, and it's always best to address human factors as they are the most critical factors in developing such systems. In the CyberSecurity 470 course, a final project is required for a group of 4 students to develop an idea that relates to human factors in cybersecurity. And my group decided to do a project on the least significant bits in image steganography as our final project. I'm very fortunate to have Professor Ruspa Hafnazar Kochesarai as my professor for the course, as he has a wealth of knowledge in this area and in engineering in general. And I am very happy, very lucky to have him as my professor for this course. The Cybersecurity Engineering Department at George Mason University is very well done, a very conductive environment, and I'm very happy I'm a student in the departments, as I believe they are the most sought after knowledge experts in the field of cybersecurity engineering. In my group, there is other members that include Andrew McConnell, Mira Aldaba, and Sara Aldaba, that all 4 of us contribute to this final project. So, first part of this presentation, I want to do an introduction on image steganography. Image steganography is the use of an image to store secret data, explicitly embedding such data within an image file. There's multiple methods in which this can be done. One is through the Unicode, which is the code instructions to display a file. Such code includes displaying certain pixels that display the image itself, which have a finite amount of pixels. It generates an image that's in a JPEG or a GIF file. Another way is to change the color of the pixels themselves, which for our project we directly change the color of the pixels through a secret key algorithm. And there's other ways as well to hide images and data and information within images and image files. Steganography contrasts with encryption. Encryption secures data through converting it to unintelligible text or symbols. Steganography is different. Steganography is hiding information in plain sight. So for this case of image steganography, we attempted to hide information that's in an image file. So an individual would not recognize something's hidden in the image at all. It would just appear as a regular image to an individual. The field includes many applications, including compressing data, enhancing user privacy, and securing communications outside the use of encryption. Primarily securing communication as some data may not be encrypted or may not be very effective to encrypt. So using steganography might be a better method of securing such information. My group planned to investigate the image steganography method using MATLAB code. MATLAB is a programming language in which, using number analysis and mathematical functions, you can readily code a process, such as converting pixels to different colors. Other programming languages could have been used, but I think MATLAB would be the most responsive to our needs as image steganography in our method using secret keys and mathematical conversions made MATLAB the most applicable programming language to use. So as in our project, we completed a literature review that we took multiple articles. One was about image and regular steganography in general. Other parts were about more specifically how you would complete image steganography. Many authors explain like kind of general, generic. Others became specific methods. So one example was a research team split image steganography into symmetric and asymmetric approaches. And symmetry and asymmetry is a crucial factor in encryption and in secure messaging. Symmetric messaging being that the key to encrypt and decrypt, or the key to make the data secret and make the data not secret, is the same key, the same process. Usually this is in terms of a private key. So you have a private key pair in which the key to encrypt the data and to decrypt the data are the same key. An asymmetric approach would be you have two keys. You have a public key, which you and another person would know. And then you have a private key, which only you know. And then a public key would be shared publicly on the internet, but while you keep a private key to yourself, and the private and public key pair would encrypt and decrypt data. In the case of steganography, it wouldn't necessarily be encryption, but it would be the functions or the method to hide and seek information within an image file. Would either be different or it's the same depending on the method used. Researchers are increasingly using image steganography, using very little source change from the image themselves. Wu, Yang, and Li from 2018 described that you can readily change the image by very, very, very minuscule percentage, and you can hide a lot of information by a very, very small change to the picture itself. In the application of artificial intelligence, in the fields of both cryptography and steganography, AI and machine learning have both increased the complexity and the security of steganography and cryptography. And easier methods that utilize image steganography is what's called the least significant bits, the LSB, when modifying the bits, the ones and zeros, in an image file that represent data. Usually this includes changing the leftmost bit in a single pixel, meaning that it is you plus adding 1 to that number, that bit pixel. Meaning that's incredibly invisible to the human eye. Very, very, very small change that can hide a significant amount of data within that image file. In the proposed method, the way we thought about this is use image, edit, and change some of the pixels, and have a key for this encryption process. The change of pixels will not necessarily be random, but follow a specific format designed by the sender that will contain the hidden image, the hidden message within that image. The sender would need to provide a receiver with two pieces of information. The sender would first provide an image that is slightly different from the original image, and the receiver of the message will have the original picture, the picture with no hidden message, and the edited picture with the hidden message. By comparing both the original and edited pictures, the receiver of the message will get to know what pixels were changed. The second piece of information the sender needs is to provide the receiver with the key to decrypt the message. Once the receiver is able to detect the alteration done by some of the image pixels, he or she can use the key as a translator and hence understand the hidden message concealed in the altered image from the original image. The group used MATLAB to accomplish technique of this particular technique of image steganography. In this slide, this is the design architecture. My colleague Andrew McConnell developed this flowchart that describes the process that he and the group developed for this image steganography technique. The chaos function, which shows how the pixels are changed from the original image to the altered image, which goes to the message, which is the message that the sender wants to convey to the receiver, the image itself, the stenography tool, the image out, the Stegel image, which is the altered image, and the key, the private key that the receiver uses to decrypt the message in the image. Andrew McConnell did a video on this, which I will attach in this video, that he gives more of an apt description of this design architecture that he made. For the implementation, the group, following the proposed method, created the process that the proposed method describes. Our program takes a photo and copies it into the .pmp, the bitmap file format. Bitmap images lose less data when transferring it between sources than JPEG images. When we tested this idea with JPEG images, there was more of a loss of data than using bitmap images. And the bitmap image contained more data than a JPEG image could contain. The process then takes a message and reads in all the characters in the image into their 7-bit ASCII code representations. The ASCII code is a table of values that represent a character in the English language. So A, B, C, D letters, punctuation, and so on and so forth. Like a specific number represents a character in the English language. We used a vector of strings to store each of the ASCII values. After that, the limits of blue, red, and green were stored into a vector as well. For the chaos function, we used MATLAB's built-in rand function, and we used two different functions, one for the x-axis and one for the y-axis. The proper numbers to recreate the function are written to a key.txt file. Then for each character, the program parses through and finds the xy coordinate based on what was found in the chaos function and stores the current ASCII bit into the least significant bit of the blue, red, or green field in that particular pixel. After every value had been stored, the program writes to the modified image. The resulting pictures are near impossible to see any doctoring or changing of any sorts, so using the least significant bits, while easy to implement and recreate, provides a lot of stealth when it comes to human perception. As you see for the next slide, there'll be two images and virtually no difference from the original and altered image. As you can see, here's the original image and this in the Stegel image or altered image. As you can tell, it's virtually the same image from this distance. The only way you can figure out what pixel was changed is using the tool and the key that gives you the x and y coordinate of the pixel. And an image with thousands of pixels like this image, it would be virtually impossible to figure out that altered pixel without having the key to locate the changed pixels and therefore to decrypt the message hidden inside the image file. And here's another example where virtually there's no difference between the two images, and you must have a key to find the pixels that are changed so you can find the information within the image file. So for the conclusion, through the process, the implementation itself went very smoothly. The only pertinent issue affecting the implementation of the group's least significant bit was decimal information used in the MATLAB programming language. In MATLAB, there was limits to how precise and how small a number can be. The smaller the number gets, the more processing power it takes for MATLAB to compile the code. So when we tried using a more accurate precision, it took much, much longer to compile and run the code for the image process. For the most part, the process went smoothly. In some rare occasions, the process corrupted the data based on a random number due to this precision error. In all, the group was able to implement a least significant bit image steganography process using MATLAB code. The research defined a chaos function to create the private key function of the image steganography method was straightforward, and the group faced no significant amount of challenge to use the chaos function. The program the group conceived works for any message and image input, which proved successful in the application of our research to various other fields. And with the group process using a fairly simple process of image steganography, the group hopes to further investigate more advanced methods of image steganography in the future. And through the final project, the group learned a tremendous amount regarding steganography and encryption. As students in the CyberSecurity program at George Mason University, we hope to continue to learn more about the human factors in cybersecurity engineering and other compartments of engineering, especially applied to cybersecurity. Thank you for listening to the presentation.
Hi, so I will be talking about our model and the implementation of our steganography project. So this is the model we came up with. Our steganography project, the implementation is right here. These are the things surrounding it. Actually, the chaos function is a part of it too, but I popped it out just to explain it a little better. So as we look around the classes that are in and or depend on or are dependent of our project, we have our image, which has a length, width, and depth, and we can index it, get its size, and view it. Our message has a length and contents that we can view. I will talk about the chaos function in a second. Our key has two functions. So the chaos function, I will explain, it has an x chaos function and a y chaos function. So what we want to do with the key is store the rates and then the starting x and y that we have. I'll show the actual chaos function in a graph example in a minute, and then also the length of the message. So that's why it is dependent on the message. Our stego image is a generalization of our image because it is the same image, but it has minor bit modifications that we've made to implant the message. And then our message out is what we get from using our key and then doing what we did in our steganography tool backwards to get the message. So for the chaos function, we have our rates, which are between 3.57 and 4, which I'll demonstrate why that is the case here in a second. And then we have our current x and current y, which are a rate, or not a rate, but a floating point number between 0 and 1. And then with our chaos function, we can find the next one by plugging it into the function, which I'll show here. So I have this is the chaos function. Let me see if it has the, yes. So the next iteration is equal to a rate, some rate alpha, times the current value, which is n0, times 1 minus the current value. And this, let me set this at, let's say 0.5. It acts very normally. It acts normally between 0 and 3.75, it levels off at some value until it gets to around 2.75-ish? Yes, so it levels off to 2 values, and then as we get further, or closer to 3.57, it will level off to 4 values right there. And then once we get to 3.57, you will see it spazzes out a little bit. So that's our randomness. That is how we're going to find each and every XY value pair and insert our bits. And we can choose a different starting value. See, it's very different each time. If we go back down here, it levels off at some value. If we do the 2, it still levels off at those 2 values with a certain cosine sine kind of wave function there. But we really want this randomness. So if we pick a random number, you can just get a random string of numbers, of coordinates. So our steganography tool has the image and the copy of that image, which is going to be our stego image. This is our so our limits. The array is basically, so we chose to do a ratio between the bits. We're going to store half the bits in our message into blue, the blue field of RGB in the depth of the image, a quarter into red, a quarter into green. Because a paper we read specified that the human eye can't see it cannot sense minor changes to blue like it can with minor changes to red or green. It's very hard to see changes in blue. So that's why we picked that ratio. The key is our key. We're going to have a key instance in our steganography tool. The message, the coordinates, which is our chaos functions, next x, y, and then ASCII list. So actually, we're going to use the next x and the next y multiplied by the length and width, because it is a floating point number between 0 and 1. We just want a kind of percentage length and the percentage width to go down. ASCII list is just the list, is our message encoded into ASCII code. So the operations in our steganography tool are, we copy the image, which it takes an image and it creates our, it doesn't create our stego image, but it turns into our stego image. It becomes our stego image. We write our key to a file, so our key is going to receive the rates and then the starting x and y value, so we can recreate the function in our message out function, where we take the stego image and a key and we create the message from it. We have our rand and rand rate, which create the current x, current y, rate x and rate y. Find limits, which is going to it's going to divide the amount of bits in our message by 4, set it to red and green, and then divide it by 2, set it to blue. Red and green should be the same, give or take 1. Next coordinates is the next bit we're going to check and we're going to possibly replace, and that's what we find with next x and next y. So check bit is going to be our LSB kind of checker. So if the bit we're trying to implant is 0, for example, and we go into the image and we find the length and width with our next iteration x and y, and that bit is a 1, or we check it, an easier way of checking it is to check if it's odd or even, and if it's odd and our bit is 0, we're going to change it to a 0. Same if our bit is a 1 and the RG or B value is even, we're going to change it. But if they're the same, we're going to leave it the same because it's already the bit we want it to be. So I will move to the implementation. Right in this section, I really like MATLAB's ability to group code in these little segments, so I can show them each and group them each by their functionality. Like each group has about the same functionality. So we read in a file name. so I can change this. I have two pictures, smoke and Milky Way. So I read in the file name into a string because I do want to change it eventually. Or I don't want to change it, I want to add it to a different file name so I can copy that image, but it still has the same image name, it just has an underscore mod. Anyways, we read in the image, we read in the message and its contents, each character, and then I'm going to make a binary contents array and make sure that each one is 7 bits, and it's going to be all of our contents but in ASCII. We're going to make a workspace folder and put a new file, which is just a copy of our image, underscore mod.bmp, and then we read it into the program, and we find its size, which is right here. It's going to be yxz, and then we open our key. This is where we find our limits. Blue is half, green and red are a quarter, and then we put it into an array. This is the chaos, where we find our current x and current y by using our rand function, and then rate x is our rand, but we do between 3.57 and 4. And then we output that to the key, which is formatted like this: rate x, rate y, current x, first x, first y, and then the length of the message in bits. And then this is where we implant our message. I'm just going to go over the blue. So we go for each each byte. It's kind of a byte. It's 7 bits, almost a byte in our binary contents. So I have to do each, for another for loop was 7, so I can go through each bit. So that's why we set it right here. We find the height and width by doing the ceiling of our current y, current x, because we don't want a 0. MATLAB does not start with 0. It doesn't start with 0 because it's more math, more akin to math than programming. So we don't want 0, so I set it to ceiling, so we always get a 1, between 1 and 789. And then this is the blue. So we're going to check blue first. If blue amounts, if we have enough more, if we can put more into blue, we're going to do blue first, and then red and green. We're going to check if that value in that position, the blue value, which is RGB, so if number 3, if it's even, on our bits odd, we want to change it. We're going to add 1. Else, if it's the value at the position is even, or odds rather, if it's odd and our bit is even, we're going to subtract 1. Same goes for red and green. And then at the end of our for loop, we want to do the chaos function. We're going to set it to the next 1. It's going to be rate x times current x times 1 minus current x, same with y. And then after all that's done, we write it to the image file. And then I'm going to run it real quick, so I can just run it in reverse. This is the message, lorem ipsum, key, and this takes in the key and the stego image, and it's going to reconstruct the message. I'll show you that it doesn't necessarily reconstruct it very well. I'll tell you why. But first, let's go through this. It reads in the same file name. Reads in the key. It's going to read in the rate x and rate y, the current x, current y, and the length, and then we make the limits again from the length. And then this is just reconstructing the message. If we go to that XYZ value and it's even, we want to put a 0. If it's odd, we want to put a 1. And then we go that for red and green as well. And then we do the chaos function. So we run this. It might be good, it might be bad, we're going to see. So it's one of the bad runs. So it gets some of the message right. I can tell you quisque vestibulum is one of these. The problem is, my best guess is that it is a problem with decimal precision. I have gone through each where we do chaos functions. I've tried to put it at 8 decimal places, 8, and then we start out with 8, and we print it to 8. The key text should have 8 as well, which is why I don't do it right here. But I think that's the problem, because sometimes it turns out really good. Let me run this again just to get different values. And I'll show you it works. Lorem ipsum, let's see that dolor is supposed to be dolor, but dk. If I run it reverse again, it's gonna get the same values. Yes, so I know that the key, the implantation, everything like that works. It's just a problem with decimal point precision. I've looked up MATLAB built-in functionality. I've used some, but it drastically slows down the program to the point where I'm probably going to have to wait hours for it just to run. But there are some runs where I can get it to be almost perfect, but there are also some runs where it looks absolutely horrible. Like this looks right, but it starts off with the wrong stuff. Anyways, that is our implementation and our model. Thank you.